Hello everyone, my name is Debdut Sengupta. Currently I am working as an assistant professor in the Department of Mathematics, Salesian College, Autonomous Siliguri. Today I am going to present a very important topic related to reanalysis, which is a part of the undergraduate board of studies over here in our college, and I hope it is present as a part of the topic reanalysis overall in India. The topic name is Nested Interval Theorem. To start with this, we have few content. The first content is the definition, then example, then comes the main nested interval theorem, and the last one is some related notes. Over which, let me start with the first one, that is the definition. A family In such that n belongs to natural number is said to be a family of nested interval if In contains In plus 1 for all n belongs to natural number, which means if you increase the indices, intervals will become smaller. Means I1 will be bigger than I2, I2 will be bigger than I3, I3 will be bigger than I4. In this way, the interval will continue. Next is that the examples, because as we know, anything that relates with mathematics, if we are planning to give the definition of it, we need some examples. So this is also not any different thing, over which here also we have to give some examples. The first example that I am going to discuss is that here is that the interval In, which consists of x such that x belongs to real number and 0 less than x less than 1 by n, where n equal to 1, 2, 3 dot dot dot. That means n is a natural number. It means the first interval I1 is open interval 0, 1, second interval I2 is open interval 0 half, third interval I3 is open interval 0, 1/3. In this way, it will continue. That means it is very much clear from this is that the first interval 0, 1 is bigger than the second interval 0 half, then bigger than the third interval 0, 1/3, and in this way it will continue. Which means this family In is a family of nested, bounded, and open interval. Because why it is bounded? Because it is bounded by 0 and 1. You can say the lower bound of this interval or the family of interval is 0 and the upper bound is 1. So this is one example of open and bounded interval, nested obviously. Second, I will provide you with an example of nested, closed and bounded interval. To start with that, let me consider the family In, which consists of all such x such that x will be in between 0 to 1 by n like the previous one, but the difference over here is that here the point 0 and 1 by n will be included, which means 0 will be less than or equal to x and x will be less than or equal to 1 by n. That means the first interval I1 will become close interval 0, 1, second interval I2 become close interval 0 half, third interval I3 become 0, 1/3, and in this way it will continue. That means the nested property will remain as it is. The only difference over here is that the intervals are closed, which means we can say this In is a family of nested, closed and bounded interval. Why I am giving focus on these two words is that we will get to know about them further in this topic. That means open and bounded is important, but closed and bounded family of nested interval is very much important, because nested interval theorem in somehow relates with this family of closed and bounded interval. Now two examples I gave. Since I started giving from bounded interval, I should give an example where the family is open but it is not bounded. At the same time, I have to give another example also where the family is closed but it is unbounded. To start with the first one, means open and unbounded, I have to start with this family In, which is equal to x such that x is a real number and x is less than 1 by n. X is just less than 1 by n. Unlike the first example where x is in between 0 and 1 by n, here x is just less than 1 by n. It means the first interval I1 will be, since there is no lower bound, please be careful or please be minded over here that this family will be bounded by 1 by n, but that will be the upper bound. That means since I said n runs from 1 to 3 dot dot, that means n is a natural number, the first member of this interval will be 1 will be the upper bound, but as a lower bound there is no such lower bound for this interval. So we will write the interval in this way: minus infinity comma 1 open, then comes I2, that is minus infinity comma half open. In this way I3. That means the property of nestedness will preserve here, but the intervals are not bounded completely, though it is bounded above, but it is not at all bounded below, because there is no such lower bound. So this is a very good example of a nested bounded interval, nested open interval, which is unbounded below. At the same time, I'll provide with another type of example where the intervals are closed but unbounded. To start with, let me consider In equal to set of all x such that x belongs to real number and x less than or equal to 1 by n. It means it is exactly similar to the previous one, but the inequality will hold here. That means it is less than or equal to. So over here the intervals will be like this: I1 equal to minus infinity comma 1 closed, I2 will be equal to minus infinity comma half closed, I3 will be equal to minus infinity comma 1/3 closed. In this way it will continue, which means this family In is a family of nested, closed and unbounded interval. Now I guess I have given all the examples of, mostly I have given all the examples of nested intervals, the possible examples to be precise. First one I gave nested bounded open interval, second one nested closed and bounded interval, third one nested open and unbounded interval, and the fourth one nested closed and unbounded interval. That means now we are in a position to move on to the next step, that is the most important step of this lecture, is that nested interval theorem. It's a very important result in the field of analysis because its application is present everywhere in the field of analysis, topology, metric space, everywhere. Then let's come to the nested interval theorem. The statement says, first we will start with the statement. The statement says if close interval an comma bn such that n belongs to natural number is a family of nested, closed and bounded interval. Please be careful with this first line. In the nested interval theorem, we need to stick or we need to restrict ourselves to consider only family of closed and bounded interval. We will not consider any other type of nested family. So once again I am repeating, if close interval an bn such that n belongs to natural number is a family of nested, closed and bounded interval, then the intersection of all these intervals will be non-empty. That means intersection will become non-empty if the intervals are closed and bounded and nested. Furthermore, that means this theorem has 2 points. Furthermore, if infimum of the length, that means infimum of bn minus an such that n belongs to natural number is 0. Again I am repeating, furthermore if infimum of the length of bn minus an such that n belongs to natural number is 0, then there is one and only one point x such that x belongs to the intersection an bn. The range will be n equal to 1 to infinity. To be precise, if you ask me to short this theorem and in a precise one, then I'll speak in this way: if an bn is a family of nested, closed and bounded interval, then the intersection is non-empty, and if the infimum of their length is 0, then not only the intersection is non-empty, but also the intersection contains exactly or precisely one point. This is the statement of nested interval theorem. Now let's move on to the proof. The proof of this theorem will divide into two parts. In the first part, we will show that the intersection is non-empty, and in the second part, we will show that the intersection contains exactly one point if the infimum of the length is equal to 0. So let's start with the proof. In the proof, as you can see, or as we can provide over here, that an bn is a family of nested, closed and bounded interval. So if we draw the number line, then the first interval will be a1 b1 because that is the bigger one. Then comes a2 b2 smaller than a1 b1. Then comes a3 b3 smaller than this two. That means it will contracting. The intervals are contracting. Instead of expanding, the intervals are contracting. The first one is a1 b1, then a2 b2, then a3 b3. In this way, the intervals will contract. Now, if the intervals looks like this, then the numbers or the elements of the interval will form an inequality, and the inequality will be looks like a1 lesser equal to a2, a2 will be lesser equal to a3, a3 will be lesser equal to dot dot dot. In this way, the endpoint an will be lesser equal to bn, b1 and then b2, then b3. In this way, it will continue. So that means we got, again I am repeating the inequality, a1 lesser equal to a2, lesser equal to a3, lesser equal to dot dot dot, finally lesser equal to bn, lesser equal to bn minus 1, lesser equal to dot 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 b1. That means the starting point is a1 preserved and the end points b1 preserves. So from this inequality, it is clearly shown that the set, if we rename the set in this way, capital A is equal to ai, I belongs to natural number, which means capital A consists of all ai's, I belongs to natural number, then that A is bounded above. And by completeness axiom and the supremum property of R, we can say supremum of A exists. Of course, B1 is an upper bound because of which supremum of A exists. So let's call supremum of A equal to X. Here I know that all of you are aware of supremum. Still I have to explain what is supremum. Supremum, you can say the least upper bound. That means all the elements of the sets will be less than or equal to that supremum, but that supremum will be less than any upper bound of that elements of the set. So since I have assumed supremum of A equal to X, which means all the elements of A will be less than or equal to X, means an less than or equal to X for all n belongs to natural number. Now we will show that Bn greater equal to X for all n belongs to natural number. So let us prove this by the method of contradiction. We will assume the contrary. That means we will assume that Bm less than X. Now since X is equal to the supremum of A1, A2 dot dot A3 dot dot till An, continuation in this way. So there must exist an element, let's say AK, in the set capital A such that Bm less than AK and AK less than X. That means Bm less than AK, AK less than X. Now we have two indices over here, M and K. Now in mathematics, in analysis, whenever we encounter with two indices, we either consider maximum or minimum to restrict them or reduce them to a single index. So since here there are two indices M and K, so let Q equal to maximum of M comma K. Q equal to maximum of M comma K. Then BQ, since Q is the bigger than M, so or bigger than or smaller than equal to M, so BQ will be less than or equal to BM and AQ will be greater than or equal to AM. That means if we merge them and write a single inequality, the inequality looks like BQ lesser equal to BM lesser equal to AM, that is lesser equal to AQ. Now in between this we can remove AM and BM, we can write the interval BQ AQ, which means we have reduced to an interval BQ comma AQ, but which is a contradiction since AQ will never become greater than BQ, because AQ BQ is an interval, means AQ must be smaller than BQ. So we arrive at a contradiction. So our final conclusion is Bn less than or greater than or equal to X. Now if we merge these two, we can say an lesser equal to x and x lesser equal to bn for all n belongs to natural number, which means x belongs to the closed interval an bn for all n belongs to natural number, which means x belongs to the intersection an bn. The range of the intersection will be from n equal to 1 to infinity. This proves the first part of the theorem. Now let's move on to the second part of the theorem. In the second part, it is being stated that if the infimum of the length of the interval is 0, then there is exactly one point in the intersection. So let's continue with that. Let x belongs to the intersection n equal to 1 to infinity an bn, and another element x dash also belongs to the intersection n equal to 1 to infinity an bn. Our task is to show that x equal to x dash, so that this proof will be completed. Now, since x belongs to intersection n equal to 1 to infinity an bn, so we can say an lesser equal to x, x lesser equal to bn for all n belongs to natural number, and an lesser equal to x dash and x dash lesser equal to bn for all n belongs to natural number. Now, if we multiply the second inequality by a minus, means minus an will become greater equal to minus x dash and minus x dash will become greater equal to minus bn. Now change the inequality and write minus bn is lesser equal to minus x dash lesser equal to minus an. Now we will merge the first inequality, means an lesser equal to x lesser equal to bn, and the inequality that we occurred now, and we will obtain the inequality like this: an minus bn lesser equal to x minus x dash lesser equal to bn minus an. Next line will be, if you take the minus common, minus of bn minus an lesser equal to x minus x dash lesser equal to bn minus an, which we can convert into a modulus. That means modulus of x minus x dash lesser equal to bn minus an, obviously it will be greater equal to 0. That means we can say 0 lesser equal to modulus x minus x dash lesser equal to bn minus an. Now my point is that in the condition it is clearly stated that infimum of the length is 0, which means for every epsilon greater than 0, bn minus an will be less than epsilon for some m belongs to natural number. If bn minus am less than epsilon for some m belongs to natural number, we can use this in the earlier inequality and we can say that 0 lesser equal to modulus x minus x dash less than epsilon. Now since epsilon greater than 0 is arbitrary, so however small we can choose it may be, so we can finally conclude that x minus x dash equal to 0 means x equal to x dash, and this completes the nested interval theorem proof. So this finishes the main theorem, nested interval theorem proof. Here I want to again say that application of nested interval theorem is that the immediate application is that you can prove Bolzano-Weierstrass theorem, both sets and sequence, using nested interval theorem. You can use nested interval theorem in Cantor's intersection theorem, which is a special case of this. Then various aspects of nested interval theorem I have already explained, various application in the field of mathematics, especially pure mathematics. Now few notes, the last segment. Over here I am saying that in the notes I am saying why closed and boundedness is so important in the nested interval case theorem. Because if you consider open and bounded, the statement of the theorem will not remain same. Why? Let me produce that with an example. If you consider the family of interval in is equal to x such that x belongs to real number and 0 less than x less than 1 by n, then intersection of this family will be empty. Though in is a nested and open and bounded interval, since closedness is missing, the intersection become empty. At the same time, not only closedness is important, boundedness is also important. Next example gives the clarity for that. If you consider in equal to x such that x belongs to R and 0 lesser or equal to x lesser or equal to 1 by n, then our result will work. But if you consider in equal to x such that x belongs to R and x lesser or equal to 1 by n, then though each of the intervals are closed, but it is unbounded, and at the same time intersection become again empty. That's why closed and boundedness plays an integral part, an important part for the theorem proof. You can't change any one of them to get the desired result. So this is my presentation for today. Hope you like my video, and I will come with further videos in the field of real analysis in future. Thank you.